Imagine you get into your car and tell the GPS, "Take me to the zoo," but your finger slips and you accidentally type airport instead. 20 minutes later, you are arriving right next to a busy runway. Does this mean your GPS is broken? Not at all. The computer didn't make a mistake. It executed the exact instructions you provided, navigating perfectly to the wrong destination. This diagram shows the core operating blueprint of computing devices. It is a three-step cycle: input, process, output. In our car scenario, the incorrect location was the input. Calculating the roads was the process. Driving to the destination was the output. We tend to think of computers as intelligent, but their ability to make good decisions rely entirely on the quality of the initial instructions we hand them. This raises a serious problem. What happens to the final result if the data entering a system is inherently flawed from the very beginning? Computer scientists illustrate this equation using a rule called GIGO, which stands for garbage in, garbage out. A machine has no common sense. It cannot guess what a user actually meant to do. It blindly trusts whatever data it collects. You can build the most advanced piece of hardware in the world, but if the raw information entering the system is corrupted, the final action will be useless. Picture a smart classroom, where the real temperature is a comfortable 22 degrees Celsius, but the room's temperature sensor cracks, and it mistakenly sends the computer a reading of 40 degrees Celsius. The central processor accepts that high temperature as an absolute fact. It instantly triggers a command to run the industrial cooling fans at maximum speed. The same error happens everywhere. A supermarket scanner misreads a chocolate bar, and the register charges you for a plastic toy. Dust clouds a phone's fingerprint scanner, and it permanently locks you out of your own device. If the temperature sensor had been accurate, the classroom would be comfortable. If the barcode scanner was clean, the grocery bill would be correct. In all these cases, the processor worked flawlessly. The failure occurred at the sensory level. Even a perfect brain will make terrible decisions if its eyes are lying to it. The human body operates using the same input, process, output blueprint as a machine. Think about crossing a busy street. Your eyes act as organic cameras, and your ears work like microphones to collect data about the oncoming traffic. That is your input. That data travels to your brain, which functions as your biological CPU. It analyzes the speed of the cars and the distance of the crosswalk to calculate if it is safe to cross. That is your process. This split screen shows the final step. On the right, your brain commands your leg muscles to step forward. On the left, a computer commands its actuators, the mechanical parts that physically move, to perform an action. That is your output. Recognizing how our own biology flows from observation to action illustrates how machines perceive and react to the physical world. Let's apply this logic to an engineering challenge. You want to design an automated control system to feed your puppy. How do you build a machine that knows exactly when to drop the food without a human there to push a button? You start with a dedicated input device. A weight sensor placed under the bowl continuously measures the remaining kibble to detect the exact moment it becomes empty. The computer evaluates the data. It checks if the bowl is empty and cross-references a motion sensor to verify the pet is actually nearby, preventing the food from sitting out all day. With both conditions met, the processor generates the output. It triggers a small motor to release a precise half cup of fresh food. By combining multiple, accurate inputs, engineers allow machines to make complex decisions entirely on their own, defeating the garbage in, garbage out problem. This three-step blueprint scales up from a simple pet feeder to power the infrastructure of the modern world. Smart air conditioners actively measure room temperature to keep homes cool. Automated washing machines track water levels and spin cycles. Factory robots rely on laser sensors to assemble cars with millimeter precision. No matter how complex artificial intelligence or robotics become, every single action they take is dictated by the flow of input, process, and output. Take a look around your own home. Find your microwave, your washing machine, or your thermostat, and try to identify the specific input, process, and output of each one. Behind the illusion of a smart machine, a computer is simply waiting for you to give it good instructions.